Cindy Buxton, our presenter this evening, graduated from the University of Washington in 1990 with a master's in geology. She moved to Haines, built a cabin, and did geologic field work around the state during summers. About 25 years ago, she and her husband, Russ White, formed a consulting firm to do 3D geological modeling for mining companies such as Kensington and other companies around North America. She has learned a little about the geology of Haines by reading papers about the area and also by looking at rocks as she hiked the various trails and beaches. I believe Cindy's presentation will be about 45 minutes, followed by a question and answer session. So please keep yourself muted throughout and type any questions in the chat, and we'll try to visit those questions at the end. Okay, Cindy, take it away.
Hi, everybody. Hopefully you can hear me okay. So I decided to do these talks because after those landslides in December, I had a lot of people asking me questions. Unfortunately, I was not able to answer most of those questions because I'm not a landslide expert. So I thought it would be helpful if I did these two talks and introduced people to the geology of Haines. I thought teaching you some of the terms and understanding the history of the area would help when we do have landslide experts telling us more in coming months. If you felt more familiar with the geology, you would understand what they were saying and you'd be able to ask better questions. So I hope this helps, and I apologize for not being able to answer very many landslide questions. You can go ahead and ask at the end of the talk, but I may not be able to answer them. So tonight, oops, I got to get my screen to work here. So tonight I'm just going to give an overview, and then next week, I'll talk about the rocks of Haines. And that part, I will try to help you figure out what kind of rocks are under your house, or perhaps something you're more interested in is what kind of rocks are above your house, thinking about landslides. So tonight, the first thing I want to address is why don't geologists ever seem to give straight answers? I heard quite a few people being frustrated that they felt they were asking simple questions to the geologists and they didn't give a straight answer. So I want to explain why that is, and also how do geologists figure out the geology. It's a little bit different than some other sciences like chemistry and physics, where you can answer a lot of questions in a lab and come up with very exact, precise answers. It's just not quite like that for a lot of geology. Then I'll jump quickly into talking about faults and earthquakes in this area, and then our glacier history and glacial rebound and sea level changes, and then a little bit about artesian wells. Because one of the wells on the Beach Road neighborhood became artesian during the big rains and during the landslide. Artesian means that it doesn't need to be pumped out; the water just spurts out the top. So I just want to touch on that a little bit. It's a lot to cover. The geology is far more complex than I'm going to be able to talk to you about tonight. I'm hoping that I'll have time next fall to do a whole series of lectures that delve into each of these parts as its own full lecture, where we can really get into the details like plate tectonics, glacial history, earthquakes and tsunamis, and various other things. But for tonight, it's just kind of an overview. I'm going to simplify things and skip over some stuff. But if you feel like you don't understand something, please type it into the chat and I'll try to answer it when I can. If not, I'll try to answer those questions at the end. And I will try very hard not to talk too fast, but it is a lot to fit in 45 minutes. So why don't geologists ever seem to answer simple questions with simple answers? The best way for me to explain that is with this joke. It's like the only joke that I can ever remember. In my field, I often work with engineers and geostatisticians and geologists, and we all think very differently, and that makes it really hard to work together. So anyway, this joke explains that. So say these three people go in for a job interview and the interviewer asks, what's 2 + 2? Well, the engineer might answer 2 + 2, that's 4.000. The geostatistician might say, well, what do you want it to be? Or they might ask, what was it last time? And that's because geostatistics is a bit of an art as well as a science, and it really helps to know what it was last time. The geologist would say, well, 2 + 2, somewhere between 3 and 5, pretty close to 4. Can't ever say for sure, but you need to do more studies. And you will very often find geologists answer a question and then say, well, we need to do more work on that. And it's not because we can't add, it's because the question isn't that simple. It's not 2 + 2. It's really a whole string of numbers that we need to add up to get to the answer you want. But we don't actually know what any of those little numbers are. Like at the bottom, we might know the range of what that number is, but we might not. So we have to do a lot of educated guesses. And so we know that we can't be very precise and we can't be always very accurate. And so by saying it's between 3 and 5 and close to 4, we're conveying that there's some uncertainty, and that's important to us. So how do geologists figure things out? So I like to compare it to a giant jigsaw puzzle. So you're all old enough, probably you've done jigsaw puzzles. I don't know about kids these days, but I think you're all adults out there. So you've done a jigsaw puzzles. You may have 1,000 pieces and you have the picture. So for geology, imagine that each one of those jigsaw pieces is a clue or a fact about that we're trying to use to figure out the whole story of the geology of an area. So one of those pieces might be a basalt in a particular location, or a fossil, or it might be a fault that we found someplace, or it might be a spring, like Mud Bay Spring is a clue. There's salt water in some of the wells between Mud Bay and Letnikoff. That's a clue. Where the streams are, how the rocks are distributed. Those are all individual clues. But unfortunately, if it was 1,000-piece puzzle, we really only have like 30 pieces, or maybe 40 pieces, but we don't have all the pieces. So imagine this. So say we have 30 pieces. I don't think there's 30 pieces in this picture here, but the other thing we weren't given is the picture on a box. So we've got these pieces. We know we don't have them all. We don't even know what some of them are or where they fit, and we don't have the picture. But we know, because we've done jigsaw puzzles before, we turn over all the pieces and we see some of them are sky and clouds. So we know that those are going to go on the top, right? I don't know how much you can see on your screens if you're looking at this on an iPad or something small, but the ones at the top have sky in them. And then there's a few, like these two, that have sky and mountain in them. Okay, so, I'm going to put those pieces there. I'm just kind of guessing where they go. But now I know there's mountains in the picture too. And so I put the kind of mountainy ones up in there. And then I see, this one's got a little bit of water under the mountain. You might not be able to see that. And so then I put all the watery pieces kind of in there. And because I'm a geologist, I can tell those are water. And then there's these ones down here, and those are forests. So since water was up here, maybe the forest is down here. So, you just kind of put the pieces there. And then you start kind of figuring out what this jigsaw puzzle might look like. So here I've drawn a line between the mountain and the sky, kind of having to guess a lot, but I'm fitting it around those two pieces. And then I know there's water, so I'm kind of drawing, and here it looks like there's water and mountain on that to there. And so I draw it through, and then I just have to really guess where the line between the forest and the water is. So here's kind of my lines that give me a sort of sense of the picture. I still don't know a lot, but I'm starting to get a general idea. So here's what the picture really looked like. And you can see my lines are kind of okay, but not very exact. Here it's kind of goofed because I took the water all the way out, and this is land in here, and the forest isn't quite right. But I have sort of a general picture, and so I can already say some things about what's going on. Of course, the goal is to actually get the real story and have all the pieces and really know everything. But that's never going to happen for geology. One reason is some of the pieces that we need are buried under the forest, under the trees and the moss and the soil and way underground. And we don't even know which ones have the important pieces, because there's a lot of rocks that don't tell us very much. It's only certain ones that tell us, bits of the story. And in this big valley, Chilkat River Valley, there used to be, in a that used to be all rock before the glaciers and the river. And all of those puzzle pieces with really good information are gone. We're never going to get those back. So some of the evidence or puzzle pieces have been destroyed. Some are buried in places we're never going to find them. And other pieces are just really hard to get to. I mean, we haven't had geologists walk all of these mountains. They're not very easy to walk in, and it takes a lot of time, and who's going to pay us to do it? And so there's lots of information out there we still do not have. Eventually, we'll get more. And every time we put in a puzzle piece, a good solid piece that gives us a really good clue, then it tells us more of the story. And so with time, our facts in our story get more exact and more full. So anyway, that's a long story of why geologists aren't necessarily going to give you a very clear answer, and why they use sort of general terms. And it's not because we just don't know how to add, and it's not because we're stupid, and it's not because we just don't want to give you an answer. We're doing our best. We just don't have all the information we need. Okay, so let's move on to some questions I'm hoping to answer tonight. So, there's questions like, why are the mountains and valleys there? Do I have a fault near my house? Do I have one under my house? Will there be a big earthquake? Those questions we can answer with kind of explaining the plate tectonic history of the area. So that's where I'll start. And then there's questions like, why is Lynn Canal so deep? Why is Pyramid Island there? Why is the ground behind the Lutak Road houses so steep, where all that landslides happened in December? Why is Tysanka Harbor shaped that way? And why are there so many boulders in Chilkoot River? Those are some questions that can be answered by talking about glaciers. So I'll do that next. And then hydrology, I'm really going to run out of time, but I was going to talk about why there's salt water in the wells between Mud Bay and Letnikoff, but that'll have to be another time. But I will talk a little bit about why I think Mud Bay Spring is there, and then we'll talk about some of the wells on Beach Road. And I already have a question in the chat that I'll answer when we get to that part. So that hydrology is the study of how water is flowing. Okay, so plate tectonics. So most of you know what plate tectonics is. You might be a little fuzzy on the details. If you're older than me, you might not have learned about it in school because it's a fairly new theory. But these days, everything in a geology textbook in a class relates back somehow to plate tectonics. So if you remember the Earth, there's the inner core, there's the outer core, and then there's the mantle. And the very outer edge is the crust. Crust is not very thick. Under oceans, it's about 5 kilometers thick. Under the deepest, tallest mountains, it also goes down deeper into the mantle, but it's like 70 kilometers thick. And the average land, the continent, is about 30 or 40 kilometers thick. It seems like a lot, but compared to the rest of the Earth, that's really not very much at all. So the crust is thin and it's sort of brittle, and it has broken up into what's called plates. And so the blue lines in this picture show the plate boundaries. So a plate is basically a chunk of the crust that moves around as a unit. And they're moving side by side next to other plates, and some slide under other ones, and some break in half or break apart and new plates form. And so these things are moving around, not very fast. You can't feel it happen, but in geologic time, some of it seems very fast. But anyway, so the blue lines are the plate boundaries. The yellow dots are earthquakes, and the red triangles are volcanoes. So you can see most of the volcanoes, not Hawaii over here, but most of the volcanoes and most of the earthquakes in the world are on those plate boundaries. So here is the picture of North America and the Pacific. So the Pacific plate, as it's called, is over on the left side, and the North American plate is over here. So the part that's closest to us is in the little yellow line, if you can see where my cursor is pointing. And the one you're most familiar with, the plate boundary you're most familiar with, is the San Andreas Fault. Well, so what's the difference between a plate boundary and a fault? Well, a fault is two pieces of land that are moving in different directions from each other. So there's lots of friction in between them. One side might be going up and down or just sliding sideways. And as they're sliding past each other, it can cause earthquakes. A plate boundary is just like a giant big asphalt. It goes really deep into the crust, whereas most faults that are not on plate boundaries don't go nearly as deep. So the San Andreas is a plate boundary. So like San Francisco is on the edge and it's basically on the Pacific plate, and Los Angeles is on the Pacific plate, and the rest of California is on the North American plate. So the Pacific plate is moving up to the northwest. The North America plate is moving in a different direction, slower and slightly to the west and a little to the south. So what's shown on this picture is parts of this fault. When they break, only parts break it at one time. So imagine having two wood blocks covered with sandpaper that you're pushing towards each other, against each other fairly hard. And now you try to slide them past each other. There's a lot of friction. And if you push hard enough, you're not able to slide it very much. And as you keep pushing and trying to make it slide, suddenly it will slip and move suddenly. And that sudden motion is what an earthquake is. It's when these two bits of land are kind of stuck and not able to slide past each other, but the forces are wanting them to slide. And so suddenly it overcomes friction and it slides fast and it moves. And then that's the earthquake. But not the entire fault moves at the same time. So you see parts have moved in this graph at different times, and the like M79 is the how big the earthquake is, and the big number is the year. And part of this in the black, that doesn't have much friction, that little section, so it's just moving really slowly every year. Anyway, that's not too important to this story, but I just wanted to explain that to you. So that was down here, San Andreas, if you can see where my cursor is, hopefully. If we move up that line, that white line, we get to the yellow line. And so that's all basically the same. It's basically the San Andreas Fault. It's just called different things on different sections. So the yellow line there is called the Queen Charlotte Fault. Okay, so here we are. Blue is ocean, the green is land. This is Alaska. The pink arrow is pointing to where Haines is. And this red line that I'm pointing to with the cursor is the Queen Charlotte Fault. That is the plate boundary between the Pacific plate with the ocean and the North American plate off to the east. So these are sliding past each other at a rate of about 58 millimeters per year on average on the Queen Charlotte. So we have a huge plate boundary not too far from us, just out on the ocean. And the rest of this story is for another time. There's lots of interesting things about Alaskan geology. Anyway, a long time ago, that San Andreas-like fault came up and went up this red line and basically went straight through Haines. Chilkat River goes up the Chilkat River, and then it curves all the way and goes all the way up to Denali. That is a really long fault, and that is because it used to be the plate boundary. So it used to be exactly like the San Andreas Fault. It no longer is. It is still a fault. It's still broken there, but the movement between the plates is now happening on the Queen Charlotte Fault, which is good for us, because we're not going to have as big of earthquakes in our area. The land is not moving around quite that much. So here it is looking a little bit closer into Haines. You can see where Haines is pointing. There's the town, and Clickwan is up in here, and here's the Chilkat Peninsula. So the pink line, sorry, it's a little goofy, jaggedy looking. The pink line is basically the Denali Fault. So it goes up the Chilkat River and goes all the way up to Denali. So the Chilkat Mountains used to be part of the Pacific Plate, and they used to be moving to the northwest compared to all the stuff on the other side of that pink line. So as you'll notice, those are in the valleys or in the inlets, and that's because when these two bits of land are moving across next to each other, they break up the rock in between. It leaves, sometimes they're very wide zones, hundreds of feet, not just, a piece of paper thin. It can be quite wide, and it grinds up all the rocks. And so when there's water moving over the landscape, the water flows down the hill, and it hits a stream, and the stream wants to get out to the ocean or a lake as easy as possible. So it ends up eroding out and washing away the loose stuff that was where the faults were. And so faults often end up being valleys. And in our area, general area of Southeast Alaska, whenever you have a very long, straight valley, there's a good chance that there is a fault there. It does not necessarily mean that there's a fault, but there's a good chance. So after those streams eroded, most of you know, we had glaciers in this area. So the glaciers followed the streams, and they scooped out, and they made these really big, wide valleys and scooped all of this out. So we have Lynn Canal, which is really deep, and we've got Chilkat River, and then we've got the tall mountains between them. So that's why we have the mountains where they are and the valleys where they are. It's because of where these plate boundaries are, which are now faults. So this is a diagram that I made a number of years ago. So it is no longer up to date, and I didn't have time to fix this. But this shows some of the earthquakes that have been centered in our area. So like this one that's a 3.7 magnitude, that the center of where that happened was about 5 miles below the surface and right under downtown. And so there's probably a little fault right in there. There was some earthquakes on the actual Denali Fault. This was one in 1973, and that's about where the one a few weeks ago was. It was a 2.9, and it just felt like this big jerk. Many of you felt that. It was probably about in that same place. So there were some other earthquakes, and there was one we had a few years ago or 5 years ago, way up the highway. That was related to one of these faults. So most of these are in the 3s, 4s, and 5s range, and that one a few years ago was a 6. If you'd had a 6 in New York City or San Francisco or something like that, there could be a lot of damage. Here, we don't have so much damage. One, because we don't have as many houses, but two, our houses are mostly built not too far above bedrock. And earthquakes can get magnified when you have a whole bunch of sand and gravel or fill on top of bedrock, and it just jiggles back and forth during the earthquake. And we don't have that so much here. So we're less likely to have damage to our houses for moderate size earthquakes than in some other places. So could we have big giant earthquakes on these particular faults? Probably not, because there's not as much force wanting to move things side by side and move them back and forth here. But they are weaknesses because it's all broken up. So anytime something moves someplace else, it can just kind of jiggle these, and they can move a little bit. But we can feel earthquakes from the Queen Charlotte. So you can see there's dates and magnitudes for parts of each of those faults that slid in different years. And these are the ones out here on the Aleutians. So we are within reach of feeling a lot of these earthquakes, but at least they're not right. The epicenter, the center of it wasn't, right in the middle of Chilkat River. So we will feel big earthquakes for sure. So I kind of explained why we have mountains and valleys where they are. You do have a fault near your house. You have something that used to be basically the San Andreas under Lynn Canal and under Chilkat River. Some of you do have faults under your house. And I don't have those all mapped out, and some we really won't be able to map out. But most of those are pretty small and probably not really active. They could have, they were moving around a long time ago. They're not probably moving around very much. On the left here is a picture from an earthquake in New Zealand in Kaikoura in 2017, I think it was. And here is a house actually on top of a fault. They did not know that they had a fault there. And this was a very big earthquake, pretty amazing. Anyway, you can see that the driveway got shifted over And the house, part of its foundation was on one side of the land of the fault and the other on the other side. So when the fault moved the driveway and the land, it pulled part of the house off of its foundation. The house stuck together, but it was better attached to the land on this side, so it just pulled it off. Anyway, don't think any of this is going to happen in Haines. The faults are less active, and there's some other reasons. Anyway, I think you're pretty safe from this, but we are going to have some earthquakes sometime. Sorry about that, having my phone ring. Okay, so let's move on to the glacial history. Now, remember, I apologize, I am moving pretty fast, but hopefully this all makes sense because you've heard some of it or most of it or all of it before. So glaciers, the glacier story. You all know we had glaciers here. We still have some glaciers. You may not be familiar with what things they have caused. Like, it explains why you have big boulders laying around or in the Chilkoot River, and why Pyramid Island is there, and why Tysanka Harbor looks that way, and even why Lutak, where all the houses are and the state park and everything, why it's kind of looks like that. So let's learn a little bit about let me go over the glacial history. So this is a picture of the glaciers during the maximum of the last big ice age. So about 20,000 years ago, everywhere that is purple was covered in pretty deep ice. And you can see we're right in over here. Because the ice, some of this place, it was, over a mile thick. I don't actually know the real number, but pretty thick. And that contained a lot of the water that's on the surface of the earth. So the sea level was much lower. So that's when you could cross Bering Strait to go to a picnic on the other side, and the coastline and down here in the Gulf of Mexico and eastern United States, the shoreline was much further out because the ocean is shallow there. And so as the ocean lowered, there was more land. Here's what it looked up closer. So Haines is right up here, if you can see my cursor. And so some of the glaciers came all the way out to the very outer ocean. Now this shows it all being covered, but really we had mountains sticking out through the top of this in places. But for the most part, it was all under ice. So this could be kind of like what Haines looked like at one point in time. This is a picture not from 20,000 years ago, obviously, but you can imagine that these mountains here are the Tokschnuks, and this peak is maybe Mount Rapinski, and downtown Haines is where this kind of red circle is, and Beach Road neighborhood would be down over here, and but this isn't when the ice was at the highest. Where these yellow lines are, that's probably where the top of the ice was at one point in time in this particular picture. So I want you to just be aware this isn't what Haines looked like when the glaciers were at their maximum. But one really interesting thing to see here is it's pretty steep, especially like over here above Beach Road. And this is why it's steep above Beach Road. And that was certainly a contributing factor to that landslide. The reason is that glaciers, when they move, they erode on the sides. They're rubbing on the sides, and they've got rocks stuck in them and just grinding away the rocks on the side of them as well as on the bottom. So they teach you in middle school and high school that glaciers make this U-shaped valley. And so it's very steep on the sides versus if a stream did it, it's just eroding at the bottom. So it's more of a V-shaped valley and often, not always, but often not quite as steep. Of course, it looks very different where we are because we had sea level is higher than in this picture. Here's what it might have looked like up Chilkat River. So again, the ice is not at its highest, but say this was Chilkat River and Clark ones were here somewhere, and Haines is off at the bottom corner, the lower right. And there would have been glaciers coming in from all the valleys off on this side, the Kicking Horse and the Surku and everything like that. And they push out into this main river of ice. So anyway, this is kind of what it could have looked like at one point in time. So it's hard to imagine. I mean, really, was there really a mile of ice over the top of Haines? That's really hard to imagine. But this picture is of Muir Inlet, the eastern arm in Glacier Bay. In 1941, this picture was taken, the one on the left, and you can see there's a cliff right on the edge in all three pictures. So all three pictures are taken from the exact same spot. One in 1941, that was here my dad was born. You can see there's ice, pretty thick ice. The middle picture is from 1950. That was before I was born, but you can see that it's melted back pretty significantly, but you can actually see it's still pretty high on this back hill here. And in 2004, which is a few years after my daughter was born, the ice is all gone. You can see where the ice used to be over here in this picture where it's all white. And there's a side glacier off over there. I think it's the Riggs Glacier. Anyway, just in a span of, 2 generations or even one full generation. My father just died last year. So in one person's lifetime, you made these huge changes. That is really, really fast. Didn't happen that fast in Haines, but I just want you to see, to believe for your own eyes that there really can be that much ice and it can all disappear. Okay, so just going to teach you a little bit about how glaciers work. Very, very simple stuff. So up in the mountains where it's colder, it snows year after year. If it doesn't melt in the summer, then it accumulates more and more and more. And eventually there's so much snow that it compresses the bottom part to ice, and ice can start to flow and it wants to move downhill. So then it starts moving downhill and it's eroding things, and things are falling off the mountains and it moves down. Ice always moves downhill. It does not move uphill until it reaches the front. And at the front, the melting, it's melting all over, but here the melting is happening as fast, or at the rate that it's moving forward. So it's got this face here. If it's melting faster than it's moving forward, then this nose or front of it moves backwards. And if it's moving faster than it's melting, then it moves forward. So here's a picture. I don't even know where it's from. You can see I got it off the internet. There's rocks that basically fell off the sides of the hills, and you see all these boulders here, and it's all dirty. That's all dust and dirt, and there's all sorts of dirt and dust and boulders inside the glacier too, because through time, it got more snow on top and built up higher, and rocks got buried. This is a picture that, I don't know, either Russ or I took. We were flying with Paul Swanstrom a few years back, the day after this big giant landslide, which came off the top here, and it came out onto this glacier. And so I put this in here just so you could get a sense of how much erosion and how much material happens around glaciers. They're cold. They cause water to get into cracks and freeze and break. So it weakens the rocks, it oversteepens things. So there's more landslides. And then these glaciers carry a huge amount of material. So here's another diagram off the internet. Imagine the ice is flowing from the right towards the left. You can see that there's all sorts of rocks and gravel on the bottom. And oops, I'm coming down to see if anyone's got any questions here. And then you see that there's rocks incorporated in the ice. And at the front of the glacier, rocks are, it's melting. And so the rocks fall out. And if the front of the glacier has stayed in one spot for a long time, then it makes a big pile. If it is slowly melting back at the time the rocks are falling out, then it just leaves a layer of rocks, not just a big hill. This is really important for Haines, the story of understanding how things that we see in Haines. So here's one of those places where there was a big pile. You can see that it's called the terminal moraine, and you can have several of them, many of them. It's just a place where the front of the glacier sat in the same place for a long time. And so any rocks that fell onto the ice, they got carried down and then fell off the front and just leave a big pile. If the glacier keeps melting back, then it's just going to leave the rocks all scattered around. Anyway, the terminal moraines, we have a number of those in Haines, and I will show you those. Okay, so here's what some of those terminal moraines can actually look like in real life. So off to the right, you see a man standing on this very steep hill. There's big boulders and lots of gravel. The glacier has melted back since this big hill was made. The ice was much higher at that point. But a person wouldn't be walking on this when it's right up when it's being formed, because it'd be a really dangerous place to be. Anyway, big rocks. And here's one on the upper left, another terminal moraine that this man is standing on. Again, this is a picture off the internet. And back behind him, you can see this land, and there's just, rocks just scattered, but there's not a big pile. So the glacier sat in this one spot and dumped all these rocks into this pile, the terminal moraine. And then the glacier sped up and just melted away and just left this big layer of rocks. This is a picture of Davidson Glacier. We took this in 2008. The glacier has retreated, sadly, way back further up. But you can see this is basically a terminal moraine. Oh, look at all this loose rock and material. And this dark spot, there's actually a little iceberg or remnant of ice stuck in there. And that's why it's all wet. It's all wet and dark. Anyway, this didn't make a one tall, big pile. It left kind of this broad pile. So, and very irregular too. Just another thing to keep in mind. The other thing that you can see at Davidson Glacier that can give us a clue about what glaciers do and help us figure things out is the glaciers often leave these scratches. They're called striations, glacial striations. So the glacier had rocks embedded in the bottom, frozen into it, and it's moving. It scraped off all the dirt and soil and trees and bushes and got down to the solid rock and just scratched it. So if you see these scratches like this, it's they could be several different things, but one thing it could be is that it was where a glacier edge was. So back to the same picture. How do we know? How do we know that this is what it looked like? How do we know that there were big glaciers over the town of Haines? So imagine that as another jigsaw puzzle that we're putting together. So what are the clues? So this is a picture we took. I think Russ took this. This is at De La Suga, which is the near Seduction Point. These big layered rocks here, and then here's this big ass white boulder of granodiorite that did not fall off this little hill here. They're different kinds of rocks, and it didn't come from over here, and it didn't come from near Seduction Point. It didn't come from over here, and the ocean didn't wash it up. The ocean doesn't move big rocks like this, and there's no stream nearby. Where did it come from? Well, it had to be dropped here by a glacier. It probably came from 20, 50 miles upriver. Don't really know. But water did not move this here and did not fall off the hill. It was dropped by a glacier. And you see these a lot. You do not see these in Houston, Texas, where there's never been glaciers. But you can see them in places where glaciers have been, and they're called glacial erratics. Anyway, this piece by itself equivocally tells us there was a glacier here, a big glacier at some point. Another piece of evidence, jigsaw puzzle piece that tells us there was a glacier here. This is a picture I took from a kayak at low tide between Mud Bay and Seduction Point on the beach. And you see it's really smooth. And it's got these grooves. Those are glacial striations. So the glacier was sliding past this and just scratching and digging out these big grooves. The picture on the right is a picture of our son Eli. He's now 25, so this was a long time ago. Maybe he's not 25. Anyway, you can see he's standing up at Mount Riley. If you go up the Mount Riley Trail to the highest point and you turn off to the right and walk out there a little bit, this is what it looks like. And you see it's kind of smooth under his feet. And of course, it's looking out up over the Chilkat River. Anyway, there are little scratches on the rock there. They're not as nice as these ones that I took the picture of at Davidson Glacier, but they're hard to actually see in a photograph, but you can see them in person. They're there. So that tells us that at one point, the top of Mount Riley was under a glacier. So this is a picture, the Chilkat Mountains in the background and our peninsula, Chilkat Peninsula in the foreground there. I think this is taken from the Katsahine or something, or a boat. Haines is off to the right. Seduction Point is right down here at the far left. And you can see that the Chilkat Peninsula is very smooth. compared to the Chilkat Mountains. And that's because it was completely under ice. It smoothed it out and eroded it. Whereas these sharp peaks at the Chilkats, they were sticking out of the ice. And the ice level was somewhere down, above where the green is there, maybe about where the cloud is. Below that, it's kind of smooth, and above it, it's pretty sharp and spiky. So here's my little cartoon. It's totally not to scale. I'm not a very good artist, but so imagine cutting through from the Chilkat Mountains over to the mountains, on the other side of Lynn Canal, the Coast Range, and imagine Mud Bay Spring is right down here, and here's Mount Riley. So the ice went from about 3,500 feet on the shoulder of Chilkat Mountains all the way over Haines and Chilkat River and Mount Riley, and all the way over Lynn Canal, all the way over to the Coast Range. Now, it wasn't necessarily one glacier. There were all these strands of glaciers coming in that were flowing next to each other, like a river. You have streams coming in, and then they become one. So the ice thickness was, 3,500 or 4,000 feet above sea level now, but it actually also scooped out deeper. So Lynn Canal, and this is really exaggerated. So it's not really quite that deep. But it scooped that out too, and it scooped out the Chilkat River pretty deep, and it scooped them out because that's where those faults are, which I should have drawn on this picture but didn't. So it was just easier to erode and scrape things out in there than on top of Mount Riley or the mountains. But then what happened for the Chilkat River is when the glacier melted back, it left lots of sediment and washed it in and filled it up. So Chilkat River is not as deep as Lynn Canal because it's filled up with a lot of silt. And in the area of Klukwan, there's some testing that shows that the amount of silt down in there is on the order of 1,000 feet of sediment above the surface that was where the glacier was scraping it clean. So I'm just guessing that at Mud Bay Spring that maybe it's 1,200 feet thick, but that's just a guess because geologists like to guess. So if you're looking from the top of Mount Riley again up the Chilkat River, the glacier was like from this red line. So the yellow line is about where the top of the glacier was at its maximum, and it went all the way across over to the Tokshnik Mountains. It didn't go over the Tokshnik Mountains, but over to that edge. So Mount Riley was under, and this valley was under, but these mountains were peeking out on the sides. So what are some of the features formed by the glaciers? So, eroded things, made things really steep. It left boulders on beaches. This is a picture from somewhere on the peninsula towards Tyasenka Inlet. And you see this kind of weird looking thing. If you've been there, it's got lots of big boulders on it. And that is basically a terminal moraine, like this man is standing on. You see these big rocks. The glacier at that point, when it was forming this, was just stuck here at the opening, and it wasn't all the way up high. It was, I don't know, a couple hundred feet higher than the terminal moraine. I don't know. But in there, and so any rocks that fell down on the glacier flowed down on the glacier and then dropped off the front of it and made this big pile, and it goes deeper too. And then as it melted, it washed out this one side. So water flows in and out that way. Just the same as Pyramid Island. If you've been there, it's very bouldery. It's really steep. I mean, it's kind of surprising how steep it is. And it's basically a terminal moraine. And it went all the way from this beach we all love to go walk on, all the way over to Pyramid Island, and then all the way across to the other side. Here's what that looks like in map view. So the blue line is where that terminal moraine was. So the glacier was stuck right there. The front of it was right there. Rocks were just being dropped off the front. Sea level was way lower. So this might not have been water at this point. I don't know, because it is melting. And so then the glacier retreated further, and a lot of water, and it washed out the sides. So the only thing left is the part that's at Pyramid Island. And it's been filling up with sediment. And if you've looked at charts of the topography, this is much shallower and it's much deeper off the front of that. This is because it's filling in this part first with sediment. So Pyramid Island used to be a terminal moraine, and it tells us there was a glacier there too. This is a picture I stole off the internet. I'm sorry to whoever's it was. They're flying in an airplane from Skagway to Haines and looking up Blue Tack Inlet. So you can see over here, and the houses are all in the front there. And it's very steep behind those houses. And that's part of why there were some slumps and landslides and mass wasting there. And then there's Chilkoot Lake back there. Here it is in another view on the left, a map view. This is from Google Earth. So the houses are all on this shoreline over here, and then Chilkoot Lake, and then the stream through that. And this is the upper right is what the stream looks like. And there's lots of boulders. So again, it was a terminal moraine. At least this is my theory. I don't know that anybody's published this in a paper or anything, and there's certainly people who are more expert about this than me, but it looks to me like it's a pretty big, wide terminal moraine, a little bit more like Davidson Glacier, just leaving this big, wide thing. So the glacier is just slowly retreating, leaving a lot of rock here, and then it retreated further. And then all that water filled the lake because it had scooped it really deep there. And then the water needed to flow through. As the water flowed through, it washed all the sand and gravel, but the big rocks couldn't be washed downstream. So they just kept working down, and then they got, eventually there was a whole bunch of these big rocks. Now there is in the oral history, there's a story of a big rock falling into Chilkoot Lake. I don't know how many years ago. Other people know better than me. But then the story is that there was a big wave that washed through and washed out the little village that was there. And I had somebody tell me, I don't know who, but the story is that afterwards there were a lot more big rocks in the stream. And I think that could just be from more silt and sand being washed out by that big wave. I don't believe that wave washed these boulders in. I think it washed the stuff away and exposed more of the boulders. Anyway, that's my idea. But it explains, this being a terminal moraine explains why it's so steep behind these houses. And it's much more complicated than that. There's a lot. This was a beach at one point as well, it looks like, and there's lots of sand. And so it's more complicated. But I think ultimately that it was a terminal moraine. So the ice advanced about 26,000 years before present, and about 20 to 18,000 years ago, the ice was at its highest. Haines had maybe about 3,500 feet above it, but it also eroded down, so there was maybe about 5,000 feet or so of ice. About 17,000 to 15,000 years ago, there was very rapid melting of the glaciers, and the valleys were pretty much ice-free from about 14,000 to 15,000 years ago. He melted all that ice all over the world, and that caused sea level to come up. So at about 20,000, so the bottom axis here is thousands of years ago. So on the right is 0. As you go to the left, it gets older. And then change in sea level is on the vertical axis. And all these different colors are points that they've figured this out from different places in the world. So those are the data points. So this is a global sea level rise. And then they fitted this black line to it. So from when the glaciers were their biggest until about 7,000 years ago, we had about 122 meters, or about 360 feet of sea level change. So everywhere on the Earth, the sea level rose by that much. And then from about 7,000 years till present, it's just gone up a couple meters. But most of that change was between, say, about 17 and about 7,000 years ago. So sea level was coming up. But the other thing that was happening here, that wasn't happening in places like Texas or Mexico or whatever, is we had so much ice that it compressed the crust and pushed it down into the mantle. It was so heavy. It's kind of like, you have a big queen size mattress and you use your fist and you push down as hard as you can in the middle, and it pushes it down. And you'll notice it doesn't just push down right under your hand, it kind of drags the stuff near it down as well. And then you lift up on that and it wants to bounce back up. But of course, this is the Earth. It doesn't just bounce back in an instant, it takes a pretty long time. So from work that John Norton has been doing, John here in Haines, and he's been working with Jim Buxton, if I pronounce that right, and other people, they've started to pin down some things. So about 14,000 years ago, we know that the big valleys didn't have ice anymore. There were still glaciers coming off the sides of the mountains, but the middle of Chilkat River was no longer ice, and Lynn Canal was no longer ice. Part of that evidence is fossils that John collected and sent off to Jim, who then got them dated. This is a picture of a foram, which is a little micro fossil that John found in some sediments up on, I think, the property at the Miles at 25 Mile Haines Highway. And it was dated about 13.1 thousand years ago. So this little foram, that is something that forms in the ocean. So that meant that piece of land at 25 Mile, which I think is at 250 feet elevation now, was under the ocean 13,000 years ago. So we had between 17,000 and 7,000, sea level rose by 360 feet, and between 17,000 and 9,000 years ago, the land bounced back up from that big ice age. Now, this is different than the rebound that we're having now. So just remember that. Jim said he thinks it's around, Jim Buxton, around 400 feet. He's kind of the expert, and John is working with him and collecting data, and they're figuring it out. Anyway, so the sea level is coming up, but the land is coming up faster. Another piece of evidence that we have that things around Haines were underwater. This is a LiDAR picture. This is Mount Riley Road. You see this long line. LiDAR is just an aerial photo that subtracts out all the trees, and you get a very detailed picture of the topography. I can't really explain to you how it's taken, but you guys probably are familiar with it because we use this, or they use this during the landslide stuff to figure things out. It's very, very useful. And in places like Alaska, there's not very much LiDAR data, so it's really beautiful to have some now. Anyway, so White Rock Nursery is over here, and you go up Mount Riley Road. The sledding hill is right over here, and you see these funny features. I don't know if you can see them, whatever device you're on, but there's these sort of gentle curving lines through here. Those are actually old beaches where the waves kind of pushed all the sand up into a little bench, a little ridge. Beach terraces, they're called, and these ones here are about 300 feet elevation. So that means that everything under about 300 feet in Haines was underwater at one point in time. And we know that some of it was underwater at around 13,000 years because of the work that John Norton has done by collecting those samples. So that's everything under the 300-foot level is like in the middle of that orange kind of. So everything there is underwater. Well, what does that, who cares, right? Well, that tells us why there's all these sand deposits by the fairgrounds, and that blue clay that a lot of you have found if you've dug holes on your property. It's kind of this grayish, bluish clay layer that was formed when this was underwater. And that's important because that slumping thing that happened out here on Front Street, that clay layer is very thick over there, and it got a lot of water in it because of all the rains, and it just turns that clay to soup. And so then the weight of all the other ground on top of it just made the land start to slump and slide downhill. That happened in 2012, and then it happened this year. And that's why they had to do the the harbor the way they did instead of just putting piles of rocks, because they knew that clay layer was under there, and if they put a lot of extra rock on it, it might not be very strong. It's very weak, that clay layer. Now, just because you're under 300 doesn't mean you have a thick layer of clay. In some places it's thicker, in some places it's less thick, some places you have more sand. But anyway, all of that was underwater at some point in time. And everything below 300 feet. So this is a graphic sent by Jim Batesville to John Norton. So this, you can see Cluck1 is where the end of this red dot arrow a little bit, and Mosquito Lake. I might not have the exact locations, right? It's a little hard to tell. And Chilkat Lake. And so the gray is the land, the topography, and the blue is water. So he basically used a computer program to flood the topography that we have today up to 300 feet. So you can kind of imagine 13,000 years ago about where there was ocean water. And I didn't know it was that far. Probably most of us didn't realize the ocean went all the way back up in here. Anyway, this is a work in progress. I think Jim Batesville is in the middle of writing a formal paper on some of this stuff using John's fossils. And anyway, details over this story are going to change as more data is collected, but it just gives us a ballpark idea of where sea level was at one point in time. One reason that can be helpful to us in understanding the landslides is shown in this picture. So this is a LiDAR of Beach Road neighborhood. So this little thing right here, if you can see that, that is where you park to walk out the Battery Point Trail. And so here's some of the houses and Lynn Canal's out here. So you can see in this area right past the end of the road, there's all these little lines. Well, those are beach terraces as well. So that means, and Jim Batesville figured out that these were the top is about 12,200 years old. And that's a story you can ask me about sometime, or John Norton. So that meant that there was material in here that can be moved around by waves. So over here, it's solid rock. So there aren't beach terraces put there. But anyway, there was loose material here. It made these beach terraces, and they're still preserved. And none of us really realized it was there until we got this LiDAR, because it's showing very faint, subtle things. But if you go out walking there now, and I'm sorry, I should have thrown in a picture that Michael Belize took, and this shows these terraces. So go out and look there someday when you're allowed to walk out there. But what's interesting is that those beach terraces don't continue through the rest of the neighborhood. So either there wasn't enough loose material to make beach terraces, or there's been landslides on top since, and it buried those. So we know this little area off the end of the road, there has not been a landslide over that material for at least 12,000 years. This other part, we're not quite sure why there aren't beach terraces. Could be that there's been landslides, could be there's not material. Anyway, at least the Andersons know that there hasn't been a landslide near their house right there for at least 12,000 years. So the other thing that's happened, so the ocean came up, the land came up, and then we had another little ice age from about 1300 to 1850. That's not years ago, those are actual dates. From the year 1300 to the year 1850, there was what's called the Little Ice Age, and that really affected certain parts of the world, but not all of the world. This is a picture from a paper. I apologize, I didn't write where it came from. Anyway, the blue and white is where there's ice modeled, and this is Glacier Bay. So you see Glacier Bay comes all the way out here. There's not really extra ice up in Lynn Canal or the Chilkat River. It was just over here in Glacier Bay. Huge amount of ice. And again, that pressed the crust down, and it pulled the crust in Haines down too. Remember the mattress, when you push it down, the sides kind of come sloping into where you're pushing down with your fist. So it pulled Haines down. Then the ice started to melt. And from about 1790 to present, the land has come up about in Haines about a total of 14 and a half or 14.8 feet. I'm sorry, I don't know the exact number. I didn't have time to look it up. Currently, it's coming up at about 0.9 inches per year. So over 20 years, that's a lot. And you can notice it. You don't notice it from year to year, but you can notice it over, 10 and 20 years. And studies by people like Chris Larson, who've done most of the work, they know that we're only about halfway done with that rebound, and it's going to happen for about another 500 years for about 15 more feet of uplift. But the speed at which it comes up is going to keep diminishing. So, in 200 years, it'll be happening at, I don't know, half an inch per year or something. Here's some of those graphs from one of the papers, just showing the one on the left tells you how fast it's happening in millimeters, and on the right is showing you how much total it's been in meters since 1790 is what they know now is when the land started moving back up. Okay, so that's the glacial story. It kind of explains, the boulders in Chilkoot River and the boulders around town and the various other features in town. And it explains other things too. Okay, so let me just hop really quickly to the hydrology. I'm over time. I'm really sorry. So imagine this is a cartoon of what a water table is. So imagine here's the Chilkat River on the left and Lynn Canal on the right, and here's Mount Riley. It doesn't really look like this. It's totally off scale. But imagine it rains. Rain comes down onto the hill. Part of it runs down the sides and streams to the ocean. Some soaks into the ground and is used by the bushes and trees, and some soaks in further and eventually gets down to what we call the water table. So below the water table line, every little hole and crack is filled with water. And above that, the cracks and holes may be damp, but they're not full of water. Now, it can be very much more complicated than this. And in this particular place, Mount Riley, it's solid rock. There's not layers of sand and gravel like you might find the big aquifers in Texas or Oklahoma or things like that. We don't have those big sand layers on the mountains. We might in some small places like downtown Haines, but where there's lots of sand. But anyway, and in that water table, the water wants to even out. It still wants to flow downhill. So the water table mimics the topography, but is muted. So it's not it doesn't, it's not 2 feet below the surface everywhere. The tops of the mountains, it's deeper from the surface than it is down lower. So then let's put a well in there. So let's make this Noble and Julie Anderson's well off here, this black line. So you want your well to go down into the water table so that you can pump water out. And if it's in solid rock, you have to hit a crack that has water flowing into it, because if you just hit solid rock, you're not going to have much water. Anyway, in different seasons and in different conditions, that water table is in different places. So see, I've drawn a line for the drought. It's lower, there's not as much water than maybe the normal. And when it's really, really wet, it's much higher. And maybe in December, again, this is a cartoon. This is not really what it looks like, but it'll give you a little bit of idea. So it may be that the water table raised so high that their well was only the top of their well is only slightly above that. And so their whole well, the whole pipe was filled with water. But also the water table is really high now. And so there's a lot more water pressure. So there's a lot more pressure. So it became artesian, which means that it did not need to be pumped. Water was just squirting or leaking out the top. Then as it became drier, the water table lowered down and their well stopped being artesian. And I think that was late February. I'm sorry. They told me, I forgot. Okay, let's come over and look at the mud bay spring really quick, and then I'll start answering the questions. So I believe, there is a fault over here, not too far from Mud Bay Spring, but it's in the ocean. I haven't drawn this quite right. You can't really go and put your little finger on it. But this water is flowing down the water table, and it's wanting to get towards the ocean where it's lower elevation. And it hits this fault, or this fault zone, wide zone, and it's some of that water gets pushed out because there's all this broken rock, and some of it's just going to get pushed out because of the water pressure, and it's coming up in the area where the Mud Bay Spring is. And this is my theory. And so when there's a drought, the water isn't getting pushed as much because it's just lower, so it runs lower. But that spring runs all the time, even in the middle of winter and even in the middle of a drought. So I do not believe it is a stream. The DEC thinks it's a stream because there's bacteria. I have never seen what's under the rocks and what the ground looks like where the spring is coming up, but the water is very clear and there is no sediment in it. Most of the rivers, you take a bucket full, the water is going to be kind of tannish color or brownish because of the tannic acid from the soils. And it also going to have a little bit of silt or a little bit of mud. And the Mud Bay Spring doesn't have any of that. So I am personally very convinced that it is a spring. And I believe it's there because of the interaction of the water table and that fault. Okay, so that is... that's where I'm going to stop tonight because I've already used more time than I said I would. And I want to leave some time for questions. So one of the questions from Chuck Hollenbeck in the chat is, he says that his well on Beach Road is 300 feet deep, which is below sea level. Are we to understand that the aquifer is being fed from water coming down from Mount Riley? Yes. Is the melting snow and rain locally should be feeding this? Or do we know if our local water is part of a large aquifer like the Ogallala aquifer? The Ogallala aquifer is in sand and it's very large. Ours is in solid rock. And you know, it's a fairly small, I mean, this is a very small aquifer. You know, the Mount Riley is not a very big area. So if it doesn't rain on Mount Riley, eventually we will have no water that we can reach with our wells. The reason you don't have salt water in your well, even though you're 300 feet below sea level and close to the ocean, is because that water pressure from that water table, which is higher up on Mount Riley, is pushing the fresh water into your well and keeping the salt water out. And most of the water in your well should be from that water table. If you've got water from the surface coming in, then you're going to have bacteria and maybe somebody's outhouse or from the septic tank might be getting in. So usually they put in, you know, casing, so you're keeping out the surface water and you're collecting the water at the bottom of your well. So you're getting good, clean water. So yes, it is all the melting snow and rain locally that is feeding this. It is really not coming from anywhere else. I hope I've answered that question good enough. So then Eric Hawley asks, why didn't Lynn Canal fill a lot with sediment? Well, that is a really good question. Why didn't Lynn Canal fill up just like the Chilkat River? Probably the Lynn Canal was a little deeper, and so there was more ocean, and so any sediment washed into it was carried out by the tides. And Chilkat River is probably draining a much larger system than Lutak or rivers in Skagway, and so more sediment was washing in. Any sediment washing into Chilkoot is caught by the lake. So that sediment not very much of it is getting out to the ocean. And Farabee, also a lot of the silt that's being carried down by the Farabee Glacier and stuff is settling into that harbor and not making it out to Lynn Canal. So Lynn Canal's deeper, I think, and originally, and and the waves, then the ocean can carry the silt out, and Chilkat just has a lot more silt. That's my best guess. Anyway, so it'd be fine with me if Derek can unmute everybody and people can ask questions. I don't know if we need to do a raise the hand thing or not, but if Derek can unmute people so they can ask questions. I don't think I can do that myself.
Sure, I think folks can unmute themselves. If not, raise your hand and I can see that. Anybody would like to ask a question?
If you can't, if you're unmuted, I mean, if you're muted and can't unmute, you could write a question in the chat. I have a hard time believing that I explained everything just right so that you all understand.
I don't know. That was a pretty great talk, Cindy. Thank you very much.
Thanks.
Any questions from anybody? Well,
I have a question. Sorry.
okay, go ahead, Kyle.
I'm just still a little unclear on how the fault lines form the valleys. Could you just go over that one more time?
Yes. Okay. So I'll try to get back up to that slide. So when you have faults, they're grinding past each other and really crumbling it all up. So it's very loose. It's very easy to erode. And streams always find the easiest way to get down. You know, they're going to erode down through sand easier than they're going to erode through solid rock. So the streams eventually end up where it's easiest to erode. And so they're flowing downhill to the ocean and generally following the fault zones. And then the glaciers, they're just following the easiest path. And that's usually following a pre-existing stream. And so they're following the stream and then it gets scooped out more. Does that help a little bit?
Yeah, so the fault line sort of, this is probably simplistic, but kind of crumbles things up. The water follows that path, scoops stuff out as it's over time.
Yes.
And then clears the way, and then the glaciers just follow that path of least resistance.
Yes, and it's very off. Sometimes you can't. You know, there's having a big straight valley. It may be the only clue that you have that there's a fault, unless you can get over there. You know, a geologist can stand up on a hillside and draw in faults just by looking at the topography, not even having to be there. And usually the faults are all eroded. So it's a lot of times you can't ever actually go and stand on the fault and see one kind of rock on one side and the other kind of rock on the other side. And they don't belong to each other, but they're next to each other because of a fault. But often you cannot see that because they're eroded and under the dirt or under a stream or under an ocean.
And so back to Eric's question, Lynn Canal isn't the depth is roughly comparable between the Chilkat River and Lynn Canal, but more sediment settled in the Chilkat River than the Lynn Canal because more glacier systems.
Well, I'd have to, I just made that answer up off the top of my head. Okay. That's my guess, is that the Chilkat River is draining a larger area. And there's a lot of sediment. There's a lot of glaciers up there and a lot of river valleys. And any silt coming into Chilkoot Lake is getting trapped in the lake and not washing out. So that valley is not contributing much to Lynn Canal. The Ferriby Glacier and that valley, that silt isn't making it out to Lynn Canal because it's getting stuck in the harbor. The Coxsahene is certainly washing a lot out into Lynn Canal. And you can see that from the big sandy beaches and the plumes of sediment. But I suspect that there's just more tidal flux in Lynn Canal and there's less sediment coming in. There may be another factor why the Chilkat is filled up with more sediment. I don't know. I'll have to think about it.
Okay, thank you. Wow, this is really a great talk. Appreciate it.
Oh, good.
Cindy, it looks like we have a question in the chat from Paul White.
Okay.
How long does it take rainwater to filter down to 300 feet?
I don't have the answer to that. That's the other part about being a geologist is you better be good at saying I don't know. And anyway, but as Paul is my brother-in-law, and he has a mutual friend with my husband who studies this in the desert and learns how when it rains, how long it takes to get into the water table, which is very important if you're going to have a big industry come in and start sucking water out, is how fast can it recharge. And they use radioisotopes and all sorts of crazy stuff to figure that out. And none of those studies have been done here. It could be done. It just takes some money. And I don't know. I would say it's not very long here. This is a very young aquifer. I don't even know if you can really use the word aquifer, but the water table, because we can tell a difference from when it's wet to when it's drought fairly quickly. After a few weeks of less rain, then you notice the mud-based spring is running a little slower. And that means it's pretty young. The water is moving through there pretty quickly. But I don't know if it's a year or 10 years. It's not 15,000 years.
Okay, Dawn Woodward has her hand up. Dawn, can you ask the question?
Yeah, my name's Art Woodard.
Hi.
Anyway, I was wondering if you could define the type of faults that exist on the Chilkat and Lynn Canal side. So they strike slip,
Yes.
transform.
So strike slip faults are faults where the primary movement is side to side. And then you have normal faults and reverse faults where the movement is mostly up and down. But in nature, there's a gradient. So these are mostly strike slip faults, but there's still some up and down movement with them. And I can't remember what the ratio is. It's like, 4 miles of strike slip on these faults, and maybe you've got 50 feet of vertical. I made those numbers up, but it's something like that. Mostly it's side by side, but there's some upward movement. And over a long distance, that does really make a difference. So we have had some vertical offset, but mostly strike slip.
Not to change the subject, but I thought that your explanation of Pyramid Island as part of a turbulent rain was really beautiful.
Oh, good. Thanks. I made that up. I didn't make that up, but that's my interpretation. I don't really have any proof other than what I've presented to you tonight. There's no paper out there. You can't go read in a book that Pyramid Island is a terminal moraine, or that LUTAC between the lake and the ocean is a terminal moraine. That's my interpretation, and I'm not an expert on that kind of geology. So this is my best guess. Yeah, it makes sense.
Yeah.
I don't know how to raise my hand, but I do have a question. When we look at the mountains in our local neighborhood,
Right.
At what point would be the maximum glaciation? Would it be somewhere above the top of Mount Rapinski?
I don't think so.
Rapinski is rounded on the top.
Right. Well, I don't know, I guess. I'm trying to think. I don't. Do you know what the elevation of Mount Rapinski is? I can't remember.
3,800 feet.
So I guess, it's somewhere in the 3,500 to 4,000 foot range, and somebody may actually know that number. I just don't. I didn't have an infinite amount of time to prepare for this talk. My husband says, who's another geologist, and geologists never agree with each other, but he says that yes, there was ice over the top of Rapinski, but it may not have been very thick above it.
Yeah, I had sort of assumed that I could tell that if a mountain was rounded at the top, the ice had been over the top. And if it wasn't rounded, if it was more sharp, then the ice hadn't been up that high.
That's mostly true. There's also the factor of that a lot of the sharpness is because there were other small glaciers on the side that really make it steep and eroded. So, if you, and what works here isn't necessarily the same. In Texas, if you have a rounded hill, it doesn't mean there was a glacier on top. But some of the sharpness is new processes, and some is that it just never got glaciated over the top. So sorry I didn't make that clear. I think you're probably right that ice was over the top of Rapinski.
Okay, thanks. Good talk, by the way.
Oh, thanks.
Looks like Ron has his hand up.
Just go ahead, Ron. You have to unmute yourself.
Okay, this is Diane, not Ron. Hi. So my question has to do with the rotten rock that was above the slide area. Can you talk about what causes rock to rotten, and what might we expect in these areas? I mean, obviously we've got mountains everywhere, and where might it be more rotten than not?
Right. That's a very good question. And the next talk next week, I will be talking about that more. But sort of the short answer is the rock that's above the Beach Road neighborhood is largely ultramafic rock, which I'll explain what that means next week. But there's big crystals in it. And when you have big crystals, then it's easy for water to get in between the different crystals. And then it freezes and thaws and it pushes them apart and they're more crumbly. So in this type of environment, rocks that have lots of big crystals where you can see the individual minerals are more likely to crumble than a rock like the metabasalts elsewhere on the peninsula are fine grained, dark green. You can't see any individual minerals. They are less crumbly because the crystals are small. There's other factors, but we do have a lot of crumbly rock in Haines.
Will you be identifying next week where the ultramafic may be located?
Yes. I will, I need to put together the maps that I've made over the years. I need to build that talk. I haven't done that yet. But yes, I'm going to do my best to show everybody pretty much what kind of rock is on their property, as best I know, and what's above their property. And I'll talk a little bit more about the clay maybe, or go over that again. And the sand out at Lutak, I'll kind of talk about that. So, I can't answer the landslide questions very well, but I can kind of explain to you the different kinds of rocks and why some of them might be more prone to falling apart or ending up causing landslides.
Okay, thanks, Cindy.
Uh-huh.
Yeah. My next question is that the cliff that's over behind my house at the top of Allen Road,
Right.
if I understand, is metamorphic rock. Now, is that something that might crack and fall, or is it pretty solid?
It's pretty solid. We'll talk about that metamorphic thing a little bit next week, but it's fairly solid. And that's why, you can see it forms a big giant cliff, but there is a bunch of gravel at the bottom of it too. But it is a different kind of rock. It's more solid. So I think it's a little bit safer. Of course, we had no idea that Beach Road ultramafics were that crumbly or I mean, that was a pretty huge surprise for everybody.
Okay, yeah, I noticed that Allen Road did start to form cracks that were actually not parallel to that cliff, but actually at right angles coming straight down the hill.
Now, those were in the gravel at the bottom? They weren't in the solid rock, right? They were eroded by the water running down?
Yeah, that's right.
Yeah. So that's sort of different. It's not in the solid rock, but I haven't been up there myself. I was actually out of the country, so I haven't been around to look at everything myself. And of course, everything's under snow right now, so I haven't been up there to see what you're talking about.
Yeah, they fixed it, so it's harder to see now.
Oh, right. Yeah. But yeah, I think that's just eroded from the water running, and it's not a rock problem. It's through the loose stuff, the gravel and stuff at the bottom of the hill, bottom of the cliffs.
Okay, thanks.
Yeah.
Looks like maybe Art's got his hand up again.
Okay.
Yeah, I was wondering if is mafic and ultramafic, is that like igneous rocks?
Yes, ultramafic and mafic are terms that tell us about the composition of the igneous rock, and igneous rocks are rocks.
So the ultramafic would be slow cooling.
Ultra means more, so more mafic, and mafic means lots of magnesium and iron. So it doesn't actually say anything about the grain size, but in this particular case, the ultramafic in our area is very large crystals.
Aren't the larger crystals created by slower cooling?
Yes. In a magma chamber. It was a magma chamber filled with lots and lots and lots, very unusually lots of iron and magnesium. Very weird and unusual, and form some minerals that normally don't form together. It's really a weird beast, but it is very crumbly because it's such large crystals.
I find it awesome if we can unravel these puzzles and figure them out.
Yeah. Yeah, geology is really is an art as much as a science, and you do have to make a lot of educated guesses in it, and that brings in, your ability to use your experience and your intuition to take what facts you have and build a believable and more importantly reasonable story. But it is a lot of guessing. Like I just made up the story about Pyramid Island. I mean, I couldn't read that in a book. It was just my figuring it out, and it's not rocket science or anything, but
Makes sense.
yeah.
Thank you.
Looks like Ella has her hand up.
Go ahead.
Hello, this is actually Greg. Hear me? Great talk. Thank you for your time.
Sure.
We live up here on Mount Riley Road, and I just to try to understand you about the artesian wells and your theory about the runoff and not
Right.
having a big aquifer.
Uh-huh.
We in about a 10-acre plus or minus area up here where there's 4 homes, 3 of us have those artesian wells, and with ours personally, it stays at 10 pounds per pressure all year round. We don't notice those fluctuations that they're experiencing down on Beach Road.
How interesting.
But one neighbor right nearby did not hit artesian well. So, and we all 3 of us that were lucky have great pressure. So it just to understand you think this is all just pressure from runoff and snow and rain and not a bigger aquifer possibly?
Right. Well, we know there can't be a bigger aquifer because Mount Riley is only so big. I mean, it's the whole mountain is the whole aquifer.
Mm-hmm.
Water from anywhere else can't get there at that elevation, right? So it is all coming from Mount Riley, and the only water is from rain and snow.
Cool.
I'd have to think about why you have artesian wells and the other person doesn't, and why you have artesian wells so high up. So it means there's something kind of going on with the rocks in that area and where the fractures are, and I don't know the answers.
Yeah. And because when we did our test pits for CDC for our septic system, we were less than a foot to the blue clay that seals off a lot of it, and it goes down a good ways,
Right.
So it's just very curious, but thank you for your time and clarifying that.
Yeah, I would love to come out and look at your place in this summer and spring and get a better sense of where the clay is and where your wells are, and maybe I can learn something.
Oh, absolutely. Yes, indeed.
Okay, well, I'll call you up this summer.
All right. Thank you.
Uh-huh.
Bye-bye.
Bye.
All right, any more questions? Cindy,
Okay.
do you have anything
Well,
else?
you guys all know where I live, right? You can always call me up on the phone if you have a question or have information to give me so that I can learn something. That's appreciated too.